Hello and welcome back to Build a CubeSat. I'm Manuel and today I'm going to tell you how I speedran the respin of a Compute Module 5 carrier board and got it manufactured by today's sponsor, PCBWay. As some of you know, I'm working toward a minimum viable prototype of my modular CubeSat design, which I plan to launch on a high-altitude balloon test flight in June. For that flight, I want to get 3 boards working. The first one is a minimal EPS for power distribution, the second one is a microcontroller carrier board for avionics and telemetry, and the third one is a Raspberry Pi Compute Module 5 carrier board which will serve as a payload. Now, the CM5 carrier board was the last one I tackled, and since I was already preparing an order for PCBWay which included the other boards and some CNC parts, I had to move fast and get this one in there too. And that meant no time to start from scratch. I needed something that I could build upon quickly and send out for fab. Luckily, I found the CM5 MINIMA Rev 2 by Pierluigi Colangeli, which is a well-documented open source carrier board. Also, Pierre turned out to be an incredibly helpful and kind guy, and he even sent me one of his prototypes. The Minima checked all the boxes. It's only 54 by 57 millimeters in size and comes with 2 USB ports, gigabit Ethernet, a key M.2 slot, CSI and DSI connectors, HDMI and a bunch more. Some of these features I'll need for the CubeSat, others not so much. So my plan was to strip out all of the stuff that I didn't need, reuse as much of the routing as possible, and then add some of my own stuff, like the backbus interboard connectors, the CAN transceiver and also some sensors. I also knew that I wanted to expose the second camera interface because I will be using the CM5 to take stills throughout the flight and also maybe even stream some video during the first 30 seconds or so after launch. Quick side note here, the CM5 isn't really suited for space. It draws a lot of power and it gets quite hot, so it's probably not an option for a real orbital mission. On the other hand, it is super accessible and there is a ton of camera hardware for it, and also the Raspberry Pi community is fantastic. So for me, it's a good starting point for a first payload prototype. Speaking of community, if you are into compute module stuff, go check out Pierre's repo and maybe give it a star. He has also had a batch of these manufactured by Elecrow and they are available right now for $65, which I think is a very reasonable price for a board with that many features. So if you're looking for a CM5 carrier board for edge AI, robotics or media streaming, you will find the link in the description. Also, these are only some of the use cases Pierre had in mind when designing this, and I'm sure there is a lot more that can be done with it. So let's go ahead now and take a look at that respin. This is Pierre's original CM5 MINIMA Rev 2 project that you can download from his repo, and I have opened it in KiCad 9 here. Now, just to be clear, I have never actually respun a board before, so I'm not claiming that this is the best way to go about it, but it worked pretty well for me. The first thing I did was deleting everything I knew I wasn't going to need from the schematic. And Pierre had used hierarchical sheets here, which made this step a lot easier. So I only kept one USB-C port, so this one can go. And also we are not going to need the HDMI. Let's jump into this I/O sheet here. We are not going to need the SPI connector broken out. Same goes for the I2C connector. This is the fan connector. Actually, I did keep this and I broke it out to pads. So let's just delete the connector itself here. I did keep the activity. Did I keep the activity LED? I think so, but I didn't keep the power LED. And this down here is the humidity sensor, like the environmental sensor, so we're not going to need this one. Yeah, the power buttons I'm going to change later on. I think that's it for this sheet. Next up, CSI and DSI, that is just a connector, that's gonna stay of course. And then in the PCIe sheet, we see that there is a separate buck converter down here for 3.3 volts. Because the CM5 has an onboard 3.3 volt buck converter, but it can only supply, I think, up to 600 milliamps, which may not be enough for some PCIe M.2 cards. So what Pierre has done is he included a separate 3.3 volt buck converter down here. But since in the CubeSat design we have centralized 3.3 volts from the EPS, we are not going to need this buck converter. And I think this is all for the deletion, at least, you know, the rough parts of it. Of course, this process took me a bit longer the first time around, and I'm also only just showing the rough workflow here. So yeah, but let's jump over to the board now and see if we can update the board from the schematic. Let's then choose delete footprints with no symbol and delete replace footprints even if locked. And we run this and just see what happens. And as we can see now, we have a lot of orphaned footprints, a lot of orphaned traces, I mean, because we have just deleted a bunch of footprints. Luckily, KiCad has a built-in tool to clean this up. So let's go now to Tools and then Clean Up Tracks and Vias. And here I basically checked all the boxes except the top one and hit Build Changes, which will give us a preview of the changes that this tool would like to apply. And as we see here, it's just a long list of tracks that are going to be deleted. Then we can hit Update PCB and pray that KiCad doesn't crash. And it's working, and it actually worked. Nice. So what you would do next is go through the board with a fine comb manually and basically delete all the leftover tracks and vias that the automatic tool didn't catch. And make sure that you only have that stuff left that you're going to need. I also deleted the real nice silkscreen art Pierre made with Kai Buzzard, and that honestly broke my heart a little, but I needed a clean slate. Here you can just use the interactive deletion tool to make quick work of this. I just realized that somewhere around then I also rotated the whole thing by 180 degrees because I'm trying to keep all the connectors on the X Plus side of the board, so X Plus side of the satellite. So the way I did that is I selected everything, including the locked items, then went to positioning tools, move exactly, override locks, and then just type in 180 in the rotate box and hit OK. And I think this did the trick. Once that was done, what I did next was deleting the edge cuts and bringing in the DXF I had exported from Fusion. I then tried to move the edge cuts so that the CM5 is roughly in the center of the board. Now this is actually a good moment to lock everything that you don't want to move around anymore. And the way I do this is to select everything and then unlock it first, and then go through it one by one and hit L to toggle the lock status. And as you know, KiCad by default shows these purple boxes around items that are locked. And honestly, I find these kind of distracting. So what you can do is go to the Appearance panel and then to Objects and turn off the locked item shadow, which makes it much easier to see what's going on. With the cleanup done, it was time to start part 2 of this respin, which meant changing what's necessary but not adding any new features yet, and keeping as much as possible of the routing in place. Let's quickly step through what this entailed. So first up was moving the existing camera connector over to the left a bit, ideally in a straight line to make the rerouting of the differential pairs as easy as possible. Quick tip here, if you press M and then one of the arrow keys, the mouse movement is also constrained in that direction. Next up was extending the M.2 footprint to also accept 2242 modules, which we could do because we got rid of that 3.3 volt buck converter that would have occupied that area up there. Then I changed the passives from 0402 to 0603. Since I will be hand assembling this version and I have enough space, whereas Pierre was much more space constrained and knew that he would be outsourcing most of the assembly. Next up, I want to use a regular horizontal USB-C connector instead of the vertical one. I'm keeping USB-C on this board for the moment because that kind of experimental coplanar connector I am trying out on the MCU isn't proven to work yet. Then I would really have loved to use M3 solder nuts for consistency across the CubeSat instead of the M2.5 ones. But sadly the CM5 mounting holes are 2.75 millimeters in diameter, so it's going to be M2.5 for the moment. And lastly, I replaced the dip switches with jumpers that you could just short with a jumper cable or tweezers. When all of this was done, it was finally time to start adding new stuff. Some of it I had to design from scratch, but most of it I could actually just copy over from the MCU carrier board I had finished a few weeks before. Also, a quick update before we dive into that. I have recently cleaned up the Build a CubeSat hardware repo and uploaded a bunch of new stuff. A while ago, a viewer suggested that I use proper tags and releases instead of just storing the manufacturer files in the repo, and I have done that now. So if you head over to the project on Codeberg and go to the hardware repo and then check the releases tab, you will find all the manufacturing and assembly files there, including interactive bombs and PCBWay ordering info. I have also finally started writing proper README files, and exporting these 3D views using KiCad 9's new CLI tool was actually quite satisfying. Let me know in the comments if you'd be interested in a video about that. My Git workflow moving forward will be to use branches for each new revision and then selectively merging them in when they're ready for release. I have also added releases to the structure repos, but I haven't had time to write the README files there yet. So yeah, if you want to build upon or adapt or change any of this, everything I've done so far is on the Codeberg repo. Now let's switch back to KiCad and wrap up this carrier board respin. I think I will fast forward through the next part a bit so the video doesn't get too long. So the work I was most nervous about was breaking out the second camera interface. I had never done anything like this before, but honestly it wasn't that bad because the CM5 manual is great and super detailed, and thanks to Pierre the differential pair settings were already in place. So this was mostly about finding a way to route the new differential pairs around the CM5 connector. Maybe a quick word about impedance here. Pierre used PCBWay standard 6-layer stack up, and I was going to do the same thing and had a working minima on hand, so I could be confident that the track width and spacings he used were going to work. I didn't stress too much about single-ended signals like I2C or SPI, so if a track needed to be narrower to make the layout work, I just did that. After all, this board is not going to go through any EMI testing, and I just needed to get it done. The other big scary piece of work I needed to tackle was replacing the RJ45 mag jack with a Pico blade connector. I am planning to use one of these super compact Ethernet switches from BotBlocks. They are now part of Amphenol, I think, but they actually started out as an open source project, which means that there still is a 10100 switch design that I might adapt in the future. So I needed a 4-position Molex Pico blade connector instead of the full 8-line sphere routed out for gigabit. I did keep the TVS diode though for the moment, just to save time on finding a new one that would work. Next, I added all of the stuff that I would need to integrate this board with the rest of my CubeSat bus, and I literally just copy-pasted all of this from the MCU carrier board. So this included the CAN controller and transceiver, power multiplexing, 2 INA 260 sensors for monitoring 3.3 and 5 volts, the backbus M.2 connectors, and a BNO 086 IMU. Let me demonstrate real quick how I did this on a blank project for clarity. First, I copied over the sheet files that I needed, so let's take this sensor sheet here for example. Then with both projects open, I copied over the hierarchical symbols. KiCad does complain here, but the sheet content is red. And then over in the source project, I selected the hierarchical sheet, which selects all the footprints in it in PCB-new. These I then copied over to the new project, went on to update the PCB from the schematic and checked relink based on reference designator here. And voila, the footprints are moved over. Two things to keep in mind here though. First, you will still need to reroute everything manually, so tracks and vias don't come along for the ride, unless of course you take the time to painstakingly select them too. And secondly, if any of the reference designators you're importing already exist in your schematic, things will break. So before you import anything, make sure that you annotate your schematic in a different number range than the stuff that you're importing. And so after this, I just rerouted the stuff that needed it, did the usual cleanup, the checks, and the silkscreen wrangling, and this is basically the final result. It's obviously far from perfect and could be improved in many ways, but I think it will do the job for now. Exporting the manufacturing files for PCBWay was pretty straightforward as always. I was still using KiCad 8 at the time, and so I just followed their export guide, which I have also linked to below. They would have a KiCad plugin actually, which I haven't tried, but I might check out in the future. It was only after submitting the boards that I realized a mistake that could have easily derailed the assembly process. So the global solder mask expansion was set pretty high to 0.102 millimeters. This doesn't sound like much, but it basically means no solder mask at all between fine pitched pins like on the M.2 connectors. This in turn could easily lead to solder bridges between these pins, which would be an absolute nightmare with 7 high density connectors on the board. So I changed the expansion back to 0, re-exported the Gerbers, and thanks to PCBWay's great support team, they were able to just swap in the corrected files. One more thing I had not been aware of before, so the minimum solder bridge width actually depends on the color of the solder mask. For PCBWay, it's 0.22 millimeter for black, white, and matte black, but 0.12 millimeters for all other colors. And I mean, it sounds like a really small difference, but this can absolutely trip you up when placing your order. So for this board, I went with green solder mask, so the 0.2 millimeter solder mask bridges between these pins was just fine. After all of that, the order went through fine, and I should receive these boards a few days after this video goes up, along with the Micromod MCU carrier board and the minimal EPS. So with all of this new hardware inbound, I will be putting out a few more videos focused on assembling and testing in the lead up to the test flight. One more quick note about the CM5. For now I'll just be using the stock passive heatsink, which relies on convection to carry the heat away. This will clearly not work too well in a vacuum, so the CM5 is pretty much guaranteed to overheat. What I would like to try for future testing is building a heavier copper heatsink with a thermal interface to the battery pack, basically using the CM5's waste heat to help keep the batteries warm. I have printed this quick mock-up to show you what I mean. But there still are some big question marks around this idea. For one, how do we create a thermal interface between the heatsink and the battery pack? There are vacuum-rated thermal greases like this Apiezon-H, but they are hideously expensive. Maybe though there is no way around them. And more generally speaking, does it even make sense? Because the waste heat from the CM5 could be way too much for the battery pack or not enough to even make a difference. So to figure all of that out, I will need to run some tests in a vacuum and log the temperature data. But this is something I'll get into a bit later in the year. This is actually all I have for the moment. So thanks to PCBWay for sponsoring this episode, and thank you for watching all the way through. Let me know if you liked this video, and I'll see you in the next one.